Okay, so let us talk about that now. Hello.
Mhm. Hello? Yeah.
So let us talk about expanded octate.
Okay.
Okay, so
Okay.
elements which belongs to period 3
Okay.
or ahead. Okay,
Mhm.
that means period 4, 5, 6, 7. Right. So these can have expanded octate. Okay.
Okay.
Example, chlorine. Okay. Chlorine, if you see the bonding capacity, right, is 1,
Mhm.
correct?
Yeah.
But there is a molecule called as ClO3 minus. Okay.
Yes.
So we can have this polyatomic anion that is ClO3 minus. So
Okay.
that is possible.
Yeah.
Okay. So in that case, if you see the structure, right? So
Yeah.
we'll have, or let us draw the structure. So how do we draw the Lewis structure for that? Chlorine has 7 valence electrons, one of it. Then
Mhm.
oxygen has 6 valence electrons, three of them, and you
Yeah.
have one negative charge, correct?
Yes.
One minus one charge. Okay. So you have 7, 18, and 1. So you
Mm.
have 26 valence electrons,
Okay.
correct?
Yeah.
And what does the rule say? You need to pick a central atom, correct?
Yes.
So central atom is generally the one which
Mm.
has maximum bonding capacity,
Okay.
correct? That
Yes.
is a rule that you know,
Yeah.
correct? The
Mm.
other rule that I told you, if you remember, is if you have to pick the element which is least in number in the structure,
Mhm.
correct?
Yes.
So the bonding capacity when it is a simple molecule, it works.
Okay.
Okay, but when you have a complex molecule, use the rule that I am suggesting you now. What is the rule?
The one
Least in
with
number,
the number.
right?
Yes. So.
And there is an exception to this. And that exception is hydrogen and fluorine.
Okay.
Why? Because these two are monovalent and they will never be in the center.
Okay.
Correct?
Yeah.
Okay. Have you copied all this?
Yes. I'm almost done writing. Okay. Now I'm done. Okay.
Done?
Yeah.
Hello?
Hello. Can you hear me?
Yeah, I can hear you.
Sorry, I said
So,
yeah. I'm done.
okay. So now we have the central atom chlorine,
Mm-hmm.
right? Why? Because that is the least in number.
Mm-hmm.
And then we have oxygens around them.
Yes.
Okay. And what is the rule? We give the shared pair of electrons.
Okay.
Correct?
Yes.
And then we complete the octate of the extreme atoms. Correct?
Yeah.
So if you observe 6 and 18, we are done with 24 electrons.
Mm-hmm.
Correct? We
Yeah.
have still two more remaining. So
Yeah.
those two go in the center.
Okay.
Okay, you complete the octate.
Yeah.
However, you need to remember that if any of the oxygen has 3 valence electrons.
Yeah.
Okay,
Mhm.
then it then that means it is having one negative charge. So there is a concept of formal charge which I am not explaining over here, but as a simple term, try and remember, if you see 3 lone pairs on oxygen, it counts for one negative charge.
Okay.
Okay, so this means that the current structure will be ClO3 minus.
Okay.
Sorry, ClO3 3 minus. Correct?
Yeah. I'm a
But the structure that we need is ClO3 minus. Correct?
yes.
So what we'll do in that case is we will transfer a lone pair from two of them to the center.
Okay.
Correct? Can you
Yeah.
draw that?
Okay. Okay. So yeah.
Done?
Yeah.
Okay. Now I'm erasing everything and we go back to the structure. We have chlorine, then we transferred a double bond, right?
Yep.
So, like we have a double bond over here, we had another double bond over here, right?
Yep.
And then we had one oxygen. So
Yes.
this oxygen now will have 3 lone pairs,
Okay.
correct?
Yeah.
And this will have 2 lone pairs.
Okay.
So 2 lone pairs on oxygen means the charge is zero.
Okay.
Okay. So the structure that we have now is ClO3 minus. Okay.
Okay.
However, we started the discussion with expanded octet concept, right? So
Yeah.
now you have one pair over here, second pair over here, third pair over here, fourth pair over here, and fifth pair over here.
Okay.
Correct?
Yeah.
Am I right?
Yes.
And you also had one lone pair. Correct?
Yeah. The
Please check.
lone, I'm a bit confused. The lone pair like remains on chlorine.
Yeah, it will remain on the chlorine. It was at its original place, right? And we transferred uh the lone pair from the one lone pair from the oxygen because it would have given it an additional negative charge.
Okay.
Okay.
I'm just gonna count out. Okay.
Then
Yeah.
okay. So that's done. Okay. So now if you count the total electrons on chlorine, how many of them are there? We have 12 electrons,
Yeah.
correct? And that indicates the expanded octate,
Okay.
correct?
Yeah.
Right? So there are compounds which are stable even if they have even if they have
An expanded octave.
yes.
Sorry, what does an expanded octave mean? Because I thought like they can only have like 8 in each shell.
So expanded octet is basically more than 8 electrons.
Okay.
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 Yeah.
So if we want to draw the structural formula of this compound, structural formula will be okay.
Okay.
Okay. Now I would suggest you to try PO3, PO4 3 minus.
Okay. Should I send a photo?
Yes, please. Okay, I saw the picture and it's correct. So the structure that you got is P, right?
Yeah.
Mm, right. But however, I thought that it is an expanded octet. It isn't. Oh yeah, it's an expanded octet,
Okay.
right? So there is a lone pair over here,
Mm-hmm.
and there are three lone pairs, correct?
Yeah.
On this oxygen, three lone pairs on this oxygen, right?
Mm-hmm.
So this makes it PO3 minus. And do you understand why it is an expanded octet? 1, 2, 3, 4, and 5. So phosphorus is having 10 electrons,
Yeah.
which is more than the
8.
octate of that is 8 electrons, correct?
Yes.
So there are compounds which have expanded octate,
Okay.
okay?
Yeah.
And there are compounds which have, let us go to the next concept. Uh, that is the exceptions to the octate rule. I already told you about uh, expanded octate, and there are compounds like NO2. Okay, so if we can draw the Lewis structure of NO2, right? So if we draw nitrogen, so NO2, nitrogen has 5 valence electron multiplied by 1. Oxygen has 6 multiplied by 2. So you have 5 and 12. So you have 17 electrons. So total electrons are odd, correct?
Yeah.
Okay. And if we draw the structure, central atom, let it be nitrogen. Okay. And let us have two oxygens around it. Okay, let
Okay.
us give a shared pair and complete the octate for the extreme atom,
Okay.
right? So we have used 16 and there is one lone pair on the nitrogen.
Hmm.
Sorry, not lone pair, one single electron.
Okay.
So NO2 is a molecule that exists in nature.
Yeah.
And if you notice, it is having an incomplete octate, correct?
Yeah.
And also it has odd number of electrons.
Yes.
Does that make sense?
Yeah. It has
Okay,
like 5 electrons on it. It's,
sorry.
it has like five electrons.
Yes. Okay, and nitrogen will not form expanded octate.
Okay.
Why?
Because it doesn't have more than 8 electrons for like a
No,
full.
no, no, because it belongs to period 2.
Oh, okay.
Only compounds after period 2, that is 3 and ahead, can have expanded octate,
Okay.
right?
Yeah.
There is a reason to that which we'll learn in grade 12.
Okay.
Okay,
Yeah.
because there is a concept called as hybridization. I'm not introducing that to you now, but remember, like in a simple term, if it is period 2 and lesser, the central atom will not have expanded octate. It can have incomplete octate.
Okay.
Okay,
Yeah.
uh, fine. You can draw, like take another example, that is BCl3, and share the picture with me.
Okay. Okay. I'll send it to you. Sorry, I think you're on mute.
Oh, sorry.
Okay.
The structure that you drew is incorrect, and I
Okay.
want you to guess the reason.
Okay.
Check the structure that you drew.
One, two, six. Oh, there's 22 electrons instead of 24.
Yes, this
Okay.
is what you drew. So you forgot. to complete the octate of the extreme atom.
Yeah.
Okay, so
Okay.
this is your structure. And if you notice, BCl3 is having incomplete octate.
Yeah.
Okay,
Okay.
BCl3, BF3, any example. Boron basically can have incomplete octate.
Okay.
Okay, so I believe we are done with the Lewis structure, and I can see that you are good with it. Okay, so what we need to know, we need to understand how to draw the Lewis structures, which you are good with,
Okay.
right? Now
Yeah.
you know that there are compounds which can have expanded octate. There are compounds which have incomplete octate.
Okay.
Okay, and there are compounds which have odd number of electrons.
Okay.
Okay,
Yeah.
so then this table 4 is also important because at times you get questions about the based on the properties you need to identify the type of the compound. Okay, so property state at the ambient temperature. If it is an ionic compound, it is a crystalline solid. If it is a molecular compound, it will be solid, liquid, or gas.
Okay.
Physical properties, hard and brittle, we have discussed this earlier,
Yeah.
right? Molecular compounds, solids can be soft, waxy, flexible, or crystalline,
Okay.
right?
Yeah.
Now, any molecular compound that is crystalline that is known to you, if you don't know, write down the example
Yeah.
as diamond.
Okay.
Diamond is a molecular compound which is crystalline in nature.
Okay. Mhm.
Another example I can give you is ice.
Yeah.
Then, okay, so relative melting points, boiling point, obviously ionic compounds they have high melting point and boiling point. Molecular compounds have low melting point, boiling point, except for compounds like diamonds. Okay, those are actually called as network compounds, and we'll discuss that later.
Okay.
Okay. Uh, Electrical conductivity when dissolved in water, they are really having good conductivity. Molecular compounds, they have poor. Now, for example, like here they have mentioned for most molecular compounds. That means there are exceptions to this.
Okay.
So the exception for the discussion, you can write down as graphite.
Okay.
It's a molecular compound which can conduct electricity.
Okay.
So electrical conductivity in liquid state, uh, it's a ionic compound is good, whereas molecular compound is poor. I told you about when the ionic compounds are in a molten state, they are good conductor of electricity,
Yeah.
right?
Okay. Yeah.
So example of ionic compound is sodium chloride, calcium carbonate, and for molecular compounds, you already know water, carbon dioxide, methane, sucrose.
Okay.
Okay.
Yeah.
Now the next concept is chemical bonding and electronegativity. So I want you to write down this. Electronegativity is the ability of an atom to attract bonding electrons to itself.
Okay.
Okay, so let me draw the structure of water. Okay,
Mm.
right now, if you look into the periodic table, right, hydrogen has a electronegativity of 2.1.
Mm.
Okay, and that for oxygen, I believe, is around 3.5.
Okay.
If you want to verify, can you just verify?
Mm. For oxygen?
Yeah.
Where can you find the electronegativity?
Uh, Electronegativity, where can you find? Let me see the periodic table.
Because mine only shows the atomic mass, element name, atomic symbol, ionic charge, and an ionic number.
Okay, so if we go to ptable.com, oxygen has a electronegativity of 3.4.
Okay.
Can you see? Can you go to ptable.com and move your cursor on oxygen and look on the left hand side?
Okay. Yes, it's 3.44.
Yeah. So if you go to oxygen, right,
Mm-hmm.
and the value is over here, electronegativity is 3.44.
Okay.
Okay. Mm, Let me go back. Oh, no, I lost the structure. So I said I have hydrogen, we have oxygen and hydrogen. This is the Lewis structure. If you draw it rightly, you will get this structure. I told you the value of hydrogen is around 2.1 and that of oxygen is around 3.5.
Yeah.
Okay. Now, electronegativity is the ability of the atom to attract bonding electrons to itself, right? So
Yeah.
this is a bonding electron. So this particular is a bond and the electrons involved are the bonding electrons,
Yeah.
correct?
Yes.
Now, if you notice, oxygen has a electronegativity of 3.5.
Yeah.
Hydrogen has 2.1. So that means oxygen has more ability to attract the electron. So the electron will be pulled towards oxygen.
Okay.
Okay. That means in this structure, the electron cloud is more towards oxygen.
Okay.
Okay. Or the lone pair, or sorry, the shared pair spends more time with oxygen.
Okay.
Correct.
Yeah.
Then it is spending with hydrogen. And because of that, what happens is hydrogen has a partial positive charge and oxygen has a partial negative charge.
Okay.
Okay.
Yeah.
This particular concept is called as polarization of the covalent bond.
Okay.
Okay, we'll learn this later in detail. But for now, just understand the impact of electronegativity. So what does electronegativity do?
It pulls the like we're confused. It like pulls the hydrogen closer because it
It
has
doesn't pull the hydrogen closer, it pulls the electrons closer to itself.
okay. So
Okay.
it
So the electrons are moving towards oxygen, or the electrons are moving toward the atom which has more electronegativity.
electrons.
Okay. And when you draw the polarization, you always draw it from the positive charge to the negative charge.
Okay.
And please check the tail, I have intentionally made it as positive, and the arrow is negative,
Okay.
right?
Yeah.
So when you make the arrow, remember that the tail is positive.
Mm, okay.
Can you do it for HCl and share the picture with me?
Okay. NCO.
Hydrogen chloride.
Okay, I'm sending it to you.
Hello?
Hello?
What you have written as S is actually a delta sign.
Oh, okay.
Okay, so that's fine. And the arrow that you have made is also correct.
Okay.
Okay, just I would have expect. Okay, that's fine. Whatever you drew is correct.
Okay.
Fine. So now electronegativity is a concept that is applied only to bonded electrons. Okay,
Yeah.
electron affinity is another concept that we learned,
Yeah.
right? So they are two different concepts. Okay, so the element which is on the extreme right and top is the most electronegative element. So fluorine is the most electronegative element on the periodic table,
Okay.
whereas element on the extreme left hand side bottom
Mm-hmm.
is the least electronegative element.
Okay.
So francium is the least electronegative element. Okay, am I clear?
Yes, I'm just writing it down.
Yeah. So this is the most electronegative. This is the least electronegative.
Okay.
Okay. And if you look at the trend, electronegativity goes on increasing from left to right, goes on so as you go left to right, it will go on increasing.
Okay.
Whereas from top to bottom, it will go on decreasing. Okay.
Yeah.
So now determining whether a compound is ionic or molecular. Okay. For that, there is a simple mathematical equation for delta En. So delta En is En of the element which is high minus En of the element which is low.
Mm-hmm.
Okay. So in the example of HCl, you wrote 3.16, right? Chlorine was 3.16
Yeah.
and hydrogen, I think you wrote as 2.20, right?
Yeah.
So 2.20.
Okay.
So what is the difference?
Um, is 0.96?
0.96, right?
Okay.
So you
Yeah.
know how to calculate the difference. And now let me tell you or help you how we will use this difference. So there is a electronegativity chart. So in that chart, if the value is between 0 to 0.5, okay,
Okay.
then that particular, if the electronegativity, I mean delta En, if the delta En is between 0 to 0.5, that is pure covalent. Okay, if the delta En value is 0.5 to 1.7, then it is polar covalent. Okay, and if the delta En value is above 1.7, then it is ionic.
Okay.
Can you make a note of this?
Yes.
I'll be back in a minute.
Okay.
Yeah.
I'm done.
Are you done with this?
Yes.
So this particular like chart that I gave you is extremely important. We need to use it throughout, okay?
Okay.
Right? Just remember these values.
Okay.
Okay. Now we did the example of HCl, so I'll take that example again.
Mm-hmm.
So HCl, right?
Mm-hmm.
This was a structure, right? And we know that the value is 2.20, 3.16. So we got the difference as 0.96.
Yeah.
0.96 means
It is polar
polar
covalent.
covalent. So it is covalent, but it is polar. Polar means because the value is 2.20, 3.16, difference is around 1. That means I can put a delta positive charge on hydrogen and delta negative charge on chlorine.
Okay.
If the value is zero point 0.5 or lesser, these charges are irrelevant. They are so small that they are negligible,
Okay.
right? The difference is almost considered to be negligible, correct?
Yeah.
Right? So now when it is 1, that means the charge is significant. So we can make an arrow, which is
Okay.
from the positive to negative. So
Okay.
when will you make that arrow?
When it's like significant, like when it's up from 0.5 to 1 point, like when it's up pure covalent.
When it is polar covalent.
Okay.
Okay,
Yeah.
right?
Mhm.
So this is clear.
A little bit. And I'm a bit confused.
Um, okay, let us do the example of water.
Okay.
Can you draw the Lewis structure of water?
Yeah.
Okay, and after that, identify the bonds, whether they are polar, non-polar, or ionic, and share the picture with me.
Okay. Mm,
Hello? Yeah.
mm, yeah.
So, yes, I see that the difference is 1.24, right?
Yes.
Can you again go back to the chart and see
Okay.
where, in what range is it falling?
Hydrogen is 2.2 and oxygen is 3.44.
So the difference is
Mm,
1.24.
yeah.
So which part of the chart is it falling?
Ionic, because it's above 1.7. Oh,
But
wait, no, it's polar covalent.
yes. So
Okay.
can you correct that? It's a polar covalent bond.
Okay.
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 Understood how to use it?
Yes. Yeah.
So this is what we were coming to, covalent bonds. Covalent bonds basically are formed by sharing of electrons. We know that. So there are two types of covalent, non-polar and polar. So
Okay.
if the delta values are if the delta En is between 0 to 0.5, it is covalent.
Yeah.
0.5 to 1.7,
Polar
it is polar covalent. 1.7 and above
it's ionic.
is, so
Ionic.
this is what ionic. So this is what is the chart that I
Okay.
was referring to. If you want to take a screenshot and save it, please do that.
Okay. Okay. I screenshotted it. Hello?
Yeah.
Sorry.
So is this clear?
Yes.
Okay, that's done. Now the next part is chemical formulas and formula and nomenclature.
Yeah.
So let us understand that ionic compounds. So mm, okay, so let us start from here. Binary ionic compound, a compound that consists of ions of only two elements.
Okay.
Okay, polyatomic ions. po- Obviously, as the name says, since it is polyatomic, that means it will have more than two
Mm,
elements, right?
yeah.
Oxyanions, that means it's a negatively charged polyatomic ion that contains oxygen.
Mm,
Okay, can you write down that?
yeah. Okay. I'm done.
Done?
Yeah.
Okay, after that, write down this zero sum rule. The
Okay.
statement that sum of the positive charges equals the sum of negative charges in an ionic compound. I believe you know this from your grade 10.
I think so. I'm not too sure.
That's okay, I will cover that, don't worry. So
Okay.
zero sum rule means the statement that sum of the positive charges equals the sum of negative charges in an ionic compound.
Oh,
Basically, the ionic compound is neutral.
okay. Okay. Okay.
Done?
Yeah.
Okay. Now check this example that is given over here,
Oh,
right? AlCl3,
mhm.
right?
Yeah.
Now you know that Al has three valence electrons, 1, 2, and 3.
Hmm.
Chlorine has 7 valence electrons, correct?
Yes.
Okay, so we have 1 aluminium and we have 3 chlorines,
Okay.
correct?
Yeah.
Okay, now how is this compound formed, right? So what happens is we know this is a metal,
Hmm.
right? So it will donate the electrons, correct?
Yeah.
Chlorine,
Yeah.
on the other hand, is a non-metal,
Okay.
so it will accept electron,
Okay.
correct? So
Yeah.
aluminium will donate the 3 electrons and have 3 positive charge,
Yes.
right? Chlorine will accept the electrons
Maybe three
and will have
negative charge.
negative charge. So you
Okay.
have 3 chlorine. So if you see the sum now,
Hmm.
right? So you
Right.
have 3 positive and 3 negative.
Okay.
The sum of this is 0.
Yeah.
So that is what is a zero sum rule.
Okay.
Okay,
Yeah.
right? So now you have Al2O3. You know how to guess the charges of these compound? What are the charges on them?
Um, so aluminum will give its electrons. Wait, no.
Sorry, can you be loud?
Oh, sorry. I'm gonna look at, I'm gonna draw each of them individually and then like,
No, no, I'm just asking, do you know how to identify the charges on them? You don't have to draw them.
it shows on the periodic table, I think.
No. What, when you know the formula, you
Mhm.
just cross the numbers.
Oh, okay.
So aluminium has +3 charge,
Mhm.
oxygen has 2 minus charge.
Oh, okay.
Okay.
Yeah.
So if you know the formula, you know the charges.
Okay.
And vice versa. If you know the charges, you know the formula.
Okay.
Correct?
Yeah.
Example, if I ask you potassium oxide, potassium oxide,
Hmm.
what is the formula for this? What you will do, you will go to the periodic table, find out what is the charge on potassium. Can you do that?
Calcium is It has, it doesn't show. Mhm.
So look at the bonding capacity of potassium and oxygen.
Pardon?
Hello, can you hear me?
Hello? No, sorry. I'm on potassium and it.
There's some issue with your mic. I am not able to hear you clear.
Hello? Can you? Sorry, wait. Can you hear me better now?
Let me increase the volume of my headphone. Okay, fine. Hello?
Hello?
Yeah,
Okay, now can you hear me?
yes.
Okay, sorry. Um, wait. On potassium, it's K, so the ion
What is the bonding capacity?
one. I'm not
Plus one, minus one.
sure how to like.
So if it's a metal, it is positive.
Okay,
If it is a non-metal, it is negative.
okay. Sorry, how
So,
do you find the charges? Because it doesn't show.
so bond, that is what I told you now. Look
Okay,
at the bonding capacity. If it's a metal, plus one or positive.
okay,
If it is a non-metal, it will be negative. So potassium has a bonding capacity of 1,
okay.
but it's a metal, so plus 1. Oxygen has a bonding capacity of 2.
Mhm.
Since it's a non-metal, it is minus 2.
Okay,
And then we just cross the charges
okay,
and we get the formula.
okay.
Correct?
Yeah. So metals have a positive bonding capacity while non-metals.
So don't say that bonding capacity is just a number. It tells you the number of bonds or number of electrons that they can gain or they can lose.
Okay,
But for the sake of understanding or simplicity, I told you if it's a metal, whatever is the bonding capacity, just put a positive charge.
okay,
And if it's a non-metal, whatever is the bonding capacity, put negative charge.
okay,
Okay, this is just for the sake of simplicity.
okay. So how do you find the bonding capacity? Is it through like the group number?
You remember? Yeah, group number, yes.
Okay, yeah.
So uh, if
Oh
you
yeah, now I
look at
remember.
oxygen,
Yeah,
the
so
group number is 6,
yes.
right? So the bonding capacity is 2,
Okay.
right?
Yeah. Okay, yeah, that makes sense. Yeah, I forgot. Sorry. So the first two have a plus one, like hydrogen has a plus one, and then beryllium has plus two. And then from 13 to 18, you kind of subtract.
So 13 to
17, sorry.
13 to 17, yes.
Yeah. Okay.
So no, actually from 15 to 17 you subtract,
Okay.
okay?
And then 14 is plus or minus 4.
Yes.
Okay.
1 and 2, 1 is plus 1, 2 is plus 2.
Yeah.
I'll like your group 13 is plus 3.
Okay.
Group 14 could be plus 4 minus 4.
Okay.
Similarly, there is an exception. Hydrogen,
Hmm.
okay, it can be plus 1 or it can be minus 1.
Okay.
So hydrogen with a metal like HNA or sodium hydride, sorry, NaH. Okay, sodium hydride. So
Yeah.
here although hydrogen with a metal will be minus 1.
Okay.
Okay, with a non-metal it is plus 1.
Okay.
Example, so this is NaH I told you
Yep.
and this is HCl.
Okay.
So with HCl hydrogen is positive because it is with a chlorine. So with an electronegative element it is positive. With a electropositive or a less electronegative element it is
Negative.
negative.
Okay. Okay, I wrote that down.
So that's done then. Now, can you try these compound? Practice this first and second.
Okay.
Don't do the second one because these are oxyanions and I have not covered those.
Okay. So I
But
do
just
this.
do first A, B, and C.
Okay. For aluminum fluoride, if there should be like three fluorides, do I put the three before or after the F?
Oh, sorry, your question is when
Sorry.
you have aluminium, you got the +3 charge, right?
Yes.
Fluorine is -1 charge. So you
Uh,
will cross it this way. Can you see?
yeah.
So aluminum will take the number of fluorine. So it
Mhm.
will be 1.
Yeah.
Fluorine will take the number of
Three.
aluminum.
Okay.
So your question was where will you put the negative charge, right?
Oh, yeah,
Sorry, where will you put the 3? So
Yes, it'll be
this
after.
after. So this represents 3 fluorine.
Okay,
This number represents 1 aluminum.
okay.
Okay.
Okay, I sent the photo.
Sorry. So I checked the picture.
Mhm.
Uh, MgO is correct. AlF3 is correct. K2O is correct.
Okay.
Okay. Now I want to give you the trick for the magnesium hydroxide, bicarbonates, and phosphate. Actually, the trick is that you will be all or like you will be provided with a sheet for the oxyanions.
Okay.
Okay, so like when you're school, your teacher is going to provide you that sheet. So we don't have to worry about what are the oxyanions
Okay.
or what are the polyatomic anions.
Okay.
Okay,
Yeah.
okay. So if you go to this table over here, Appendix B, page number 664,
Okay.
okay, you have the common polyatomic ions.
Okay.
Okay,
Okay.
so you will be given this common like polyatomic anions on the table. Like you will be provided with a table in the school.
Okay.
Okay, so you
Yeah.
don't have to worry about the oxyanions.
Okay.
Okay,
Yeah. So like I don't need to memorize it or
you don't have to memorize. Okay,
okay.
I'll tell you which you don't have to memorize. So you will definitely refer to the chart that your school will provide to you.
Mm-hmm.
But I'm pretty sure the bromate you will not memorize,
Okay.
carbonate you will not memorize, chlorate you will not memorize, chromate you will not memorize, chloride there is a trick to it. You don't have to memorize that. Cyanide you don't have to memorize. Uh, then okay, that's done, right?
Yeah.
So then these you don't have to memorize.
Okay.
Phosphate you don't have to memorize. Sulfate you don't have to memorize. Okay. Nitrate you don't have to memorize. So whatever is ending with ATE,
Mm-hmm.
that you don't have to memorize.
Okay.
Okay. Hydroxide you don't have to memorize.
Okay.
Okay.
Yeah.
So you will have some common. For that you will always have the table with you.
Okay.
Okay. Okay. I've stopped sharing the book with you, and I'm going to the nomenclature. Give me 1 minute. I'm searching for the notes that I have. Okay, so now am I sharing anything with you?
Not yet. I think it takes a little bit for it to show.
Now?
Yes, now I can see it.
Okay, good. Uh, Nomenclature. So now the simple rule, like what I do to remember nomenclature is that I remember the example of sodium chloride.
Okay.
Okay, so sodium is a cation, metal.
Yeah.
Chloride is a non-metal anion.
Okay.
So the rule that I know is always your metals or the cations are written first.
Okay.
Anions are coming after the cations.
Okay.
Okay, am I clear?
Yeah.
Your anions are ending with IDE.
Okay.
Okay, if it is an element, then they end with IDE.
Okay.
Okay, so can you take down these examples?
Okay. I'm done.
Done. So is
Yeah.
this simple, like based on the sodium chloride example, you need to remember cations first, anion later. The
Okay.
anions will end with IDE.
Okay.
Okay, right?
Yeah.
Can you write down this?
Okay.
Iron chloride, zinc oxide, titanium oxide, copper monoxide. Now, if you notice over here,
Hmm.
iron 2.
Yeah.
Okay, so iron 2. So this is called as IUPAC uh, nomenclature, where the charge is represented by a Roman numeral.
Yeah.
Okay, so whenever we say iron 2 chloride, we know that iron has two negative charge,
Okay.
and by default you will adjust the chlorine as per the two positive charge. Did I
Okay.
say negative for iron?
I think so, yeah.
Oh no, it's positive too.
Okay.
Okay, and you will balance the positive with the negative for the chlorine.
Okay.
Okay,
Yeah.
so for transition elements, most of the time you will have these Roman numerals indicating the charge.
Okay. Okay.
Okay, can you write down this SNO and SNO2?
Okay.
Okay. Now, hello.
Hello?
Yeah, you wrote it down.
I'm almost done. For
Okay.
the, sorry, what's
Now,
the bottom part say? Like the superus?
cuprous, Cuprous,
Okay.
and cupric. Okay. Now, I wanted to talk about that.
Mm-hmm.
This I told you is the IUPAC way of nomenclature, right?
Yeah.
And this is the common way.
Okay.
So there are two system, common system and IUPAC system.
Okay.
Okay. So if you see these names, common names, stannous oxide, stannic oxide, remember if the charge, like if you see OUS, that means it indicates lower charge of the oxidation number
Okay.
or the lower oxidation number.
Okay.
Okay. If you see the ending as IC, that means it is the higher oxidation number.
Okay.
So on the periodic table, if you go and check, tin has two oxidation number, +2 and +4,
Yeah.
right?
Yeah.
Copper has two oxidation number,
Mhm.
+1 and +2, correct?
Yeah.
So if the name is cuprous, you should know that the charge will be the
Low.
lower one.
Yeah.
If it is cupric, you should know that the charge will be the
High.
higher one.
Okay.
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 I don't think so. This has been taught nowadays in the school, but it depends on few teachers. Like if they want you to remember, or because what happens, still in our when I work in a lab, we use these terms, right? But
Yeah.
as such, as per IUPAC, ideally it is only the IUPAC nomenclature that needs to be used.
Okay.
But still, the common system is still like is being used in the day-to-day discussions.
Okay.
Okay.
Yeah. Okay. I finished writing.
And so is this clear about common system, IUPAC system for inorganic?
Yes. Okay.
Okay. Will you be able to remember the lower oxidation number means OUS, higher oxidation number means
I
IC?
see. Yeah.
Okay, good. Mm, Then this is what you should know now next. So you need to write this table, and I told you, remember, the one that is, there are few which are you need not memorize,
Mm-hmm.
correct?
Yeah.
So what I consider them as, I consider those as X.
Okay.
Okay. So X means that it is a standard on the chart.
Okay.
So I've taken the example of SO4 2 minus.
Mm-hmm.
right? Which is the standard on the chart,
Yeah.
right? So
Mm-hmm.
sulfate, that is SO4 2 minus, is sulfate,
Yeah.
correct?
Yeah.
X plus 1 indicates one oxygen more.
Okay.
So this is SO4 5 minus, or 5 minus 2, sorry.
Mm-hmm.
This is X minus 1. So it is SO3 2 minus.
Mm-hmm.
This is 2 oxygen less, X minus 2. So it is SO2 2 minus.
Okay.
Clear? So we
Yeah.
have a table where we have X, 1 oxygen more than the X, 1 oxygen less than the X, and 2 oxygen less than the X.
Yeah.
Okay? If you have 1 oxygen more, then you will add the term per sulfate
Okay.
or per dash 8. So it is, since it is a sulfate, it will be per sulfate. If it is phosphate, per phosphate. If it is chlorate, per chlorate.
Okay.
Am I clear?
Yeah.
If it is 1 oxygen less, you will write the term, change the term as ATE as ITE.
Okay.
So whenever you see ITE, what should click to you? That one oxygen is less.
Okay.
When it is hypo and ITE, you should know that there are two oxygen less than the standard.
Okay. So okay. What does the last part say? The per sulfuric acid.
Wait, no, no, that you don't write.
Okay.
Are you done with this?
Yes.
Persulfate, sulfate, sulfite,
Mm,
hyposulfite.
yes.
Okay. Now the other thing is these sulfates are also converted to acids.
Okay.
So what I have done in the next table is, or next column is, I have balanced the negative charge with the hydrogen.
Okay.
So SO5 2 minus is now H2SO5.
Okay.
SO4 2 minus is H2SO4. SO3 2 minus is H2SO3. So
Mm,
whatever is the negative charge, that is balanced by the hydrogens.
okay.
Okay. So when you do that, you get acids.
Mm-hmm.
Okay. If
Yeah.
it is a 8, the name is ic acid. So
Okay.
sulfuric acid.
Yeah.
If it is ITE, it is a OUS acid, sulfurous acid.
Okay.
So hyposulfite become hyposulfurous acid.
Okay.
Persulfate becomes persulfuric acid.
Okay.
Okay.
Yeah. Okay. I'm done.
Done.
Yeah.
Okay. Now, as a homework, I want you to do PO4 3 minus,
Okay.
ClO3 minus. So these are the X.
Okay.
Okay. PO4 3 minus is phosphate.
Mm, mm, mm.
ClO3 minus is chlorate. I want you to make this table and share with me later on.
Mm,
Okay, can we conclude for now?
yeah. Okay.
Okay, thank
Okay.
you so much for today.
Thank you. Okay. Bye.
Bye.
Have a good day.
Yeah, you too.